Hi everyone, thanks for joining us today. As you can see from this slide, my name is Richard Barry. I am a senior principal engineer with AWS IoT, IoT being Internet of Things. What you can't tell from this slide is that as an engineer at AWS, I'm actually in the minority because my software runs on the devices rather than in the cloud. These are the things that connect to the Internet of Things. More specifically, my speciality is actually in software for very small devices, microcontrollers and small microprocessors that are generally, but not always, too small to run Linux. These are the chips that are, they're sold in their billions and they surround us every day as we go around our lives. Things like fitness trackers, building control, smart plugs, and of course, many, many different types of IoT sensor in all industry sectors. I'm actually best known as the original author of the FreeRTOS real-time kernel. That is a market-leading operating system. The RTOS in there is real-time operating system. It's market-leading for this class of processor. Now, if you're used to larger processors with rich operating systems like Linux or Android, you may not recognize this as an operating system as such. If you come from the other side, bare metal, no threading, then typically you would call this an operating system. Now, millions of devices that run FreeRTOS are already connecting to AWS IoT, hence the connection between AWS and FreeRTOS, because we want to make sure that those devices can connect as quickly, but importantly, as securely as possible. So AWS IoT is obviously internet protocols, and that brings a few challenges for these smaller devices. It creates growing complexity, and we'll look at some of that complexity, where that comes from during this talk. More complexity means, of course, that it takes longer to develop. And longer to develop means that it's increasing in cost as well. So today's talk is about getting to market faster in the face of that increasing complexity. But very importantly, because we are investing more in the development, looking at what we can do to future-proof our devices as we make decisions as to which software modules to use, making sure that our devices can stay in the field once they've been deployed as long as possible and with the minimum amount of effort and rework as possible. To do this then, we are first going to look at options available to us to bring these devices into the market. And then more specifically, we will look at the criteria that allow us to assess those options for, like I was saying, the future proofing. A little bit more about FreeRTOS then. It's been in the market for about 18 years. This diagram shows the number of downloads that have been actually recorded by a third party, the repositories where FreeRTOS has been stored. So this is all third-party data. You can see it's being, downloads have gone up fairly steadily over the years. Normally, that's about all I would say with this slide, but this time I've kind of augmented the timeline along the bottom with a little bit more information where it's kind of highlighting, just generally the increasing complexity as we start from, in the early days of FreeRTOS, 8-bit devices with basic task switching. And then as we move along that timeline, we get to places where we're doing asymmetric multiprocessing and then onto even 64-bit devices, 64-bit ARM cores, 64-bit RISC-V cores. And then at the end of that timeline, we're showing kind of IoT over the last few years. So now, the complexity or the increase in complexity, which has always been there, is kind of accelerated by IoT. Whilst this slide's up, I will point out one other thing. Now, this is really so you understand the differentiation between a system like FreeRTOS and something like Linux. So FreeRTOS only uses a few tens of bytes of RAM. Now, every time you create a task, you have to give it a stack, of course. So you do use more RAM as you give it stacks, but the operating system itself uses very little. Likewise, it's like 10 to 15 kilobytes of program space. Typically, it would execute out of flash, so it would execute in place. And it is MIT licensed. So you can see, if you're thinking about open source operating systems, you're thinking Linux, it's a very, very different thing. So I've mentioned a few times then that we're getting additional complexity from IoT. Where is that coming from? Let's have a look at a kind of concrete use case here. I've chosen this. This is actually a motor control use case. I've chosen it because it's a very small application, but it's a very sophisticated application. It's very small, so we can have just a single engineer, which I've shown her here. She's an expert motor control, control theory. She's an expert software engineer, and she's writing something in software which is, creating these sine waves which are controlling this motor with a lot of accuracy, very high fidelity. Although it's high fidelity, it doesn't require much software. So I'm trying to demonstrate in this diagram that most of the software is the application software. It may even be written in assembly, right? The algorithms, although they're sophisticated, are small. It's possible that there would be third-party libraries there, maybe for fixed point math or accessing peripherals or something like that. But typically this kind of application would be responding to very fast interrupts from the motor and also timer interrupts generated on the processor itself. But the point is it's small. Now we're living in the internet age, okay? We all know that, of course. And how can we use that opportunity to take our motor and add additional real value for our customers? One of the ways we can do that is with predictive maintenance. In predictive maintenance, we are going to take data from the motor, learn how that motor is behaving, and then watch how that motor behaves to look for anomalies, and those anomalies may predict a pending failure in the motor. So this is great news for your customer. There is much less downtime. And we are predicting it's going to fail and either send a repair person or send a replacement before it fails. You can also lower your costs because if you know the health of a motor, you don't have to keep looking at it, keep servicing it. And maybe you can pass those costs on to your customer. So you can see this is, real high value functionality that we are adding. Typically, the way this would be done would be to send the data to the cloud, at least in the first instance. In the cloud, we can use machine learning to learn how the motor is behaving. We can actually pool all our data across all our motors in a single format in a single place and actually learn how to make the motors more efficient as well. So to explain this diagram here, left-hand side, that left third really in the hexagon, that's where our motor is going to sit. That is everything outside the cloud. The rest of the diagram is inside the cloud. And on the far right, we see this is where our IoT data analytics, this is where our machine learning training can be performed. So it's clear now that we've got to get data from the left-hand side to the right-hand side, and we're going through all these other pieces of functionality. Now, as is often the case with AWS IoT, those other pieces of functionality are implementations of the undifferentiating, the undifferentiating pieces that you just need. It's nothing to do with your motor control or your predictive maintenance, but they have to be there in order for you to be able to connect quickly and securely to the cloud. So here we're talking about things like the gateway. The gateway gets the data into the cloud. Authentication, that ensures that the device can trust it's connecting to the correct cloud, and the cloud knows the device is not only authorized to connect, but what it's authorized to do once it has connected. The encryption of data in rest and in flight. Very importantly, device management. So AWS IoT Core, which is the endpoint that you're connecting to here, that has more than 500 million active unique external endpoints a month, right? And 500 billion payload messages per month. You can see when you get to this kind of scale, you need a lot of help just managing your devices, onboarding them, and auditing them, that kind of thing. So that's all great. That's all provided for you in the cloud. But how do we do this on the device which is connecting to the cloud? So what I've done in this diagram is take our very, very basic motor control software and added in the equivalent device side of all that undifferentiating functionality. And here you can see the networking protocols. TLS is the security, the authentication and the encryption that we're all used to using when we connect a web browser to a website where you are authenticating it's the correct website. With IoT, of course, we want this mutual authentication, which I have already described. Then we're doing things like having to store, if we're doing authentication, we need to store the private keys and that kind of thing. So we're adding more functionality in so that we can store things securely, and then we want to be able to update it, etc., etc. You can see how this is growing. This is just another view of the same thing. Left-hand side, I'm showing the memory map for the program space, if you like, here. And we've got that small piece of functionality, and that's it. Right-hand side, showing the memory map again for the connected one, the connected motor. At the bottom, we can see the program space that functionality is using. That's increased a little bit because we are doing, maybe we are doing the machine learning inference here if we've received the model back from the cloud. And the rest of the space is this undifferentiating functionality. So this brings us on to, this is a lot of complexity that I'm an expert motor controller, but I'm not quite sure about all this other stuff that I need here. How can we manage this complexity? And I think when we get to this kind of level of complexity and this level of undifferentiating functionality, it's very easy to justify introducing multi-threading. And this is where the real-time kernel, the FreeRTOS kernel, comes in. Multi-threading gives us a few benefits here, and we can look at OTA, for example. OTA is the ability to, over the air, update a device, whether that's a new machine learning model or a new executable because you're patching a bug or something like that. With multi-threading, we can turn that into a daemon task, what we actually call an agent. This is something that just runs in the background and performs that quite sophisticated, the states and the retries and the timing for you, encapsulated in a thread, so you don't have to weave that into your application. The other thing we've done here is kind of demonstrated with the multi-threading or with the packaging of libraries together is I've just kind of blocked all that other undifferentiating functionality into a pre-packaged, I've just called it middleware libraries. And we don't really have to, well, the application writer doesn't really have to understand what is in there. And if we can pre-test those libraries, all the better. That's going to help us get to market as well. So now we kind of understand where the complexity is coming from, and we're looking at, okay, we've demonstrated slightly here that we can get benefit from having pre-packaged libraries, pre-tested libraries that we don't really have to have a lot of insight into as long as we know they're going to work. So one of the first options we have coming to market is, do we want to acquire somehow, either buy or open source those libraries, or do we want to build them all ourselves? And the trade-off here I'm demonstrating on this chart, which is a timeline starting from the left. And I've got two kind of release points here. If we move along that timeline, the first release point is if where that motor is shown, if we decide to reuse packages, either to buy them in or to reuse open source. So if we go along that timeline, we start off at the beginning with our single, expert embedded programmer. Inevitably, we are going to need more programmers. We need to integrate the package into our motor control software. We need to do lots more testing, lots more support, that kind of thing. If we take that path, and we're going to get to market relatively quickly, the other option, of course, is if you're concerned about business continuity and you want all that all that expertise and all that software knowledge in-house, you can go the other path and we carry on that timeline and we build it all ourselves. We can see that we released the product much later. We were inevitably going to be more and more, so I'm kind of stacking up the more and more software engineers as we have to get more expertise in, do more authoring of code, more testing of code. And at the end there, I'm also kind of stacking up the dollar signs and the calendars ticking away. Eventually, we get to market with all that knowledge in-house. Now here, I think you have to consider all that extra time and all that extra expense is actually developing that undifferentiating functionality. So is that a good use of time and money and delaying to market when anybody in that space is going to have to provide that same functionality? And also, because of that, there's various different products around that will give it to you already. So this is one of the decisions we have to make. And I think there are several other decisions. And I've tried to kind of categorize a few things that we want to look at here to judge these decisions. I kind of split these into two. The kind of rusty brown ones here are things that we want to consider getting our product into market as quickly as we can. I think unless we can get our product, it's a competitive world, unless we can get our product into market quickly, then perhaps making it future-proof is a bit of a moot point anyway. But the yellow ones are more to do with future-proofing. I've kind of mentioned business continuity here already. You could say, for example, do I want access to the source code? Even if I buy libraries in, I may be of the mindset that I just want to treat that as a black box. I don't care what that is. I don't even need the source code. But then you have to consider, well, if your product is in the market longer than the supplier of that code, what are you going to do? So having the source code in your pocket, so at some unknown time in the future, if you have to patch it yourself, have to support it yourself, then that may be important. But I started off talking about time to market. So let's consider that, carry on in that vein here. And all these things are about finding the right balance. Of course, there's no, like all these things, there's no right or wrong answer. With reference integrations, I think we can already tick off here the time to market. Okay, so we don't have to, they're pre-tested, pre-integrated. We don't have to write them ourselves, and other people have the tests for us. That's great. Now with FreeRTOS, you can go to the freertos.org website. You can find reference integrations there. You'll find a path to the AWS site as well, where there are IoT reference integrations in the AWS IoT device catalog. This diagram is just trying to demonstrate that all these things are packaged together. And whilst you're on the freertos.org site, have a look around, and I think that will enable us to tick off more items here. I hope you would agree. For example, you can go to the support forum and see that you can get very rapid support, very knowledgeable support, not just from the community, but also directly from the engineers who are developing the source code. So you can guarantee that it's going to be expert advice. If you're worried about IP infringement and that kind of thing, then the entire development is in a public source control repository, so you can see exactly who's writing the code and when it was added in. You can see that there's a vibrant ecosystem. And I think also, did I mention it before? It was on a previous slide. It was MIT licensed. So that's a very enterprise-friendly open source license. Now, of course, if you don't want open source, or if your company doesn't allow open source, you can go to one of our partner companies like Wittgenstein High Integrity Systems, and they will sell you a commercial license as well. And you can get commercial support from various different places. Okay, so now I'm talking about specifically like FreeRTOS reference integrations. There are other reference integrations around, not just FreeRTOS, of course. But that leads us on to, well, am I tying myself into the FreeRTOS ecosystem if I do that? Components in the market are going to change as my product is in the market. I may scale, my cost equations are going to change. And I want to make sure that I don't disadvantage myself by making decisions now that tie me in to the same decisions, in the future. So if we come back to look at actually what's inside that reference integration, we will see that actually it's all just open standards. We know TCP and TLS. MQTT is the application level IP-based protocol, which is often used with IoT. Here, actually, the OTA is specific to AWS IoT because it is fully integrated with AWS IoT device management. That gives you a lot of value, but it doesn't actually tie you in. We'll come back to that a bit later. Even when we were accessing the secure storage for the private keys and that kind of thing, we use an open standard called PKCS 11. This is a standard which is managed by Oasis. It's actually a very big standard, but don't let that put you off because we only use a small subset. It's used in laptops and that kind of thing as well. So hopefully then we are not necessarily tying ourselves in. So we can say those protocols and what have you are not, there's nothing proprietary there which is going to trap me in any way. But have we really got out of the no lock-in? What about FreeRTOS itself, the kernel itself? What about the tooling or package managers? Is there anything there which is going to be proprietary? As far as tooling is concerned, well, FreeRTOS supports or has support for more than 20 different compilers. Component support, these are the chips it supports, more than like 40 odd different architectures. And that's treating something like Cortex M3 as a single architecture. There's also a wide ecosystem, as you'll see on the website. There's a lot of people with an interest in supporting FreeRTOS. What about other tools then and package managers? Well, one of the things we've tried to do, which I will explain now in this diagram, which takes some explanation, is try and remove all dependencies, really. There is a dependency, well, there's not really even a dependency on Git because we also provide these libraries as zip files. What I'm trying to demonstrate here is some of the work that we have done to enable that, to decouple things. And if you look at the top left box, the box which is, got the kind of rusty brown color around it, that is representing the FreeRTOS account in GitHub. And the boxes that are inside it represent individual Git repositories, each one containing a single library, and those libraries are decoupled from everything other than the C library, the standard C library. I should say, actually, the TCP/IP stack in there is an older library, and that is coupled to FreeRTOS, but FreeRTOS is used with lots and lots of different TCP stacks. So on the right-hand side, the box which has the yellow outline is the same, but the AWS IoT account in GitHub. And there you will find clients that give you access to all the value-add services that are accessible in AWS IoT. We mentioned the OTA already, and we've got things like fleet provisioning and the Shadow client. Now, the white dotted lines are just showing that these libraries by themselves aren't any good. You need to have projects that build them, and you can submodule them into different projects. And I'm showing the blue, like the stacked up blue there. They show that we have also different distributions, which are one is FreeRTOS specific, and it submodules in the libraries with a load of build projects for reference integrations. And there's an RTOS agnostic one, which is in the AWS account as well. And then you can also submodule these libraries into your own application, as demonstrated in this example here. And this was like the use cases at the bottom of that previous slide. So let's say now we have our top left application, which is a very small device. Maybe this is an IoT device which is going to wake up once a day and send a message to the cloud. Maybe it's just an 8-bit device and it's able to connect because it is using a radio. Now, your product's very successful, and previously you were connecting to your own IoT service, and you know that AWS IoT is really built for scalability, so you are now going to connect to AWS. And to do that, you need to bring in either MQTT or HTTP. So you can just leave your build project as is and just build and submodule in what we call the core MQTT or HTTP library. That doesn't even depend on multi-threading. You can run it in your 8-bit environment. It's much easier to use, I should say, if you have multi-threading, for the reasons I've already spoken about. You can run it as an agent. And that will use the TCP/IP stack that you already have just by giving it the send and receive functions that you are already using. It's already connected. So now we can, I think we can tick off now the simplicity and flexibility and the portability along with the no lock-in. I hope you agree with me. So let's come back to business continuity. And this is, where having a company like AWS be the stewards of FreeRTOS adds value to the entire community. Remember, this is MIT licensed, and I've just described how there's no dependency on FreeRTOS, let alone AWS. Now, AWS, the resources AWS provide do some obvious things, like we can have additional functionality, additional chips that we support with the kernel, different libraries that we've already looked at. But there's things that are less obvious. For example, we have the automated reasoning group within AWS who are providing memory safety proofs on the code. So the new libraries have memory safety proofs, and we're building up memory safety proofs for the other libraries as well. The older libraries, starting with the attack, the strongest attack surface or the widest attack surface first, things like data coming off the network. And all those proofs run every time we check in code. This diagram actually is from a blog post on the freertos.org site that describes some of that work. There's also proofs on thread safety and schedulability, that kind of thing. Now, of course, AWS have built up great expertise, processes and practices around security for cloud customers, and we also benefit from that as well. And of course, we have long-term support releases, and with backing of a company like AWS, it adds real credibility to those long-term support promises. So this is all about building confidence, okay? And this all brings you that business continuity. So now we've ticked off business continuity and we've ticked off global presence. And that leaves us with updatability. Now, this is probably the most obvious. Hence, I've left it to last. We mentioned it before. You can't be future-proof unless you can update your device, over-the-air updates of a patched executable image, for example. Or, this also allows you to expand business models. If we think about our motor example where we were doing predictive maintenance, maybe for free you get it monitoring vibration, but if you pay more, you can send down a different model and that will monitor current and temperature as well, something like that. Here I'm showing a screen which is showing it linked into AWS IoT device management. You know that because you can see there it's offering to sign the image. Now, signing an image is really important when it's received by the device. You have to make sure that it's the genuine image and not being tampered with, of course. But I also said it doesn't tie you into AWS because you can always OTA, download an image that tells the device to then get its future updates from somewhere else. So there we are. We have ticked everything off. So that leaves with a little bit of a wrap up here. I'm not going to repeat everything, but basically what we are saying is that complexity grows all the time as devices become cheaper and more powerful. We have increased complexity with IoT. That requires us to really think about some of the criteria that I've listed here. Maybe there are more, maybe you don't agree with all of them, that we really need to consider to make sure that we protect our investment in bringing those products to market over the long term. So with that, I would encourage you to come to the website, look at what we're doing. You can look around the support forums. We keep everything open, so if you want to post a question, then you can use your GitHub account if you like. Come to our Git repository, see what we're doing. You can see what we're working on. Go to the AWS repositories. Get involved in pull requests and that kind of thing. So finally, we've all come here to learn something, of course. So there are lots more training resources. There are 25 digital courses on demand. If you go to aws.training, go to all the other talks. There are some of the topics I am showing on the screen. And finally then, I am going to say thank you. Thank you for your time. And of course, you've invested your time in coming to watch this. We want to make sure that you get a good return on that as well. We always know we can improve, so please do take the time to fill in the survey so we can serve you better next year. Thank you very much.